Well, okay, let's start anyway. Is it recording in this moment? Can you check? Okay. So, thank you very much for attending the second webinar of the internationalization pillar of the UKRAS network for robotics and autonomous systems in the UK. The topic will be related to telerobotics, teleoperation, and telepresence, robotics for teleoperation and telepresence. And we will have three guests today. Claudio Pacchierotti, researcher in haptics and robotics of the CNRS series in Rennes, France. Antonia Zemanaki, senior lecturer, associate professor in robotics at the University of Bristol, UK. And Carol Yannick, robotics and automation and technology manager at the MTC Manufacturing Technology Center of Coventry in the UK. So I think we can start immediately because we will try to have three presentations, each one of 10 minutes, followed by 5 minutes for the questions and 15 minutes final Q&A session in the panel. We will discuss mostly about telerobotics and the connections and the partnerships that can be developed on this topic between researchers and extra academic industrial potential partners outside and inside the UK. So Claudio Pacchierotti can start. Thank you very much.
Great, thank you very much, Giacinto, for the introduction. So as Giacinto said, I'm Claudio Pacchierotti, and today we'll be talking about haptics in human-centered robotics, and also focusing on the great potential of cutaneous haptic feedback. Now, before getting into this exciting topic, let me please a bit introduce myself. So my research path started back in 2012 as a PhD student at the University of Siena in Italy, wonderful city. After that, I moved to Genova. No, after that, I moved to Genova. Let me see. Yes. At the IIT Institute, Italian Institute of Technology, where I met Giacinto actually. And then I moved to the CNRS in Rennes at the end of 2016 to become a permanent researcher. Now, along all these years, my research in general revolved around haptics for robotics, from early work on robotic telemanipulation to more recent applications in air robotics, virtual reality, and microrobotics. As I mentioned, I'm part of the CNRS, which is the largest fundamental research agency in Europe, with over 28,000 researchers that address all the fields of science. Now, CNRS researchers are spread all over France and beyond, actually, with over 1,100 laboratories in France and 80 laboratories abroad. I'm based in Rennes, which is a beautiful city in the northwest part of the country. Now, I'm part of the CNRS, as I mentioned, and there I'm part of a laboratory called ERISA, in which our team, Rainbow, focuses on advancing the state-of-the-art around sensor-based robots that navigate and interact in complex environments together with humans. So we are around 50 people working on this topic. My overall research revolves around haptic science and technology, and I really wanted to briefly introduce this. Now, by analogy to optics and acoustics, haptics refers to a discipline that studies and explores the sense of touch. You can think it in this way. So in the same way as graphics and audio target a person's sight and hearing to convey, to deliver information, haptic technology target a person's somatosensory system, the sense of touch, to communicate rich information, such as the feeling of touching virtual and remote objects, or for providing navigational cues. Now, haptic feedback, so this touch information is delivered as a combination of cutaneous and kinesthetic stimuli. Cutaneous or tactile stimuli are detected by receptors located in the skin, enabling humans to perceive and recognize various local properties of objects, such as their shape, edges, temperature, and texture. Now, on the other hand, kinesthetic stimuli come from the afferent information originating from the muscles, joints, and skin. And they provide information about the position and velocity of neighboring parts of the body, as well as the applied forces and torque. So when talking about haptic technology, we refer to the capability of designing artificial systems that can sense and transmit the different pieces of information human experience physically interacting with the surrounding environment. So grounded kinesthetic interfaces are widely used in robotics. They provide compelling force feedback to the user to a desktop device that actuates a moving end effector. This end effector, as you can see, can be shaped as a handle, a pen, or a sphere. Now, these devices can be seen as force-reflecting joysticks in some way, in which the same end effector is used to control the remote robot, as well as receive force feedback about the interaction of those agents with the target environment. Grounded kinesthetic devices, such as the one that you can see here, can be have been especially used in high-end applications, such as medical robotics, space manipulation, and very much also in the nuclear industry. They provide compelling sensation, especially about shape, stiffness, and weight of remote and virtual objects. On the other hand, cutaneous haptic interfaces offer more localized feedback, focusing on tactile sensation such as pressure, texture, friction, or temperature, delivered locally, this time to the user's skin, often through moving pins or plates. Now, one of the main features of this technology of cutaneous haptics is their potential for high portability, wearability, and cost effective, especially if you compare them with grounded kinesthetic devices, the one I showed you before. And this feature very much broadens the range of applications in which haptics can be useful, revolutionizing a bit the way we can interact with everyday technology, from gaming to in-home rehabilitation. You don't hear me very well?
Claudio, it's better if you try to reconnect really quickly, possibly. Thank you.
It's a bit strange. Let me try to switch my, maybe if I remove my camera, is it better?
No. Try to relog, please.
Okay.
Thank you.
Thank you so much. I thought it was just my network.
Haptics is a key for any kind of telerobotic technology. So let's move from this. Okay, Claudio, could you try to talk now?
Is it better now?
Yeah, it's much better now.
Thank
Yes,
you.
much better.
It's great how I changed nothing. For some reason. So sorry about this.
Don't worry, it's not your fault.
So this is okay. So I think we are all convinced of the potential of cutaneous haptics. When we do research in general on haptics, this research very often stems from needs arising from very different fields of application, looking for better ways in general to interact and communicate with the human user. Now, to address these needs, researchers develop new haptic interfaces, control algorithms, as well as interaction and rendering techniques with the aim of enriching the way humans and artificial systems communicate and interact together through the sense of touch. And this is really the core of my research, like reading these needs and devising devices and rendering techniques to enhance this collaboration. And so today I will mostly, of course, focus on telerobotics. Now, in general, in telerobotics, kinesthetic haptic interfaces have been widely used, and historically, This has been the very first fields in which they've been employed. However, despite the many expected benefits, current available telerobotic systems provide very limited haptic feedback. Why is that? Well, this omission is due to different reasons, including the harmful effect that kinesthetic feedback may have on the stability of the teleoperation loop and the high cost and complexity of kinesthetic consoles. Indeed, outputting grounded forces can lead to undesired oscillations of the system, which interfere with the operation and even be dangerous in some situations. So stability control, that we all know, enables to achieve a stable interaction, but usually at the cost of a reduced transparency and realism. And of course, the complexity and cost of kinesthetic systems often limits the possibility of multi-point interaction. So for this reason, in these past few years, we have witnessed a growing interest around ungrounded cutaneous feedback solutions. So because if the feedback provided is local to the skin and decoupled from the end effector controlling the remote robot, cutaneous feedback does not affect the stability of the teleoperation loop, and it leaves it as stable as it would be without cutaneous feedback. And this is especially very promising for all those applications in which the safety of the system is of paramount importance, for example, in medical robotics. So in this respect, 10 years ago, we published one of the very first works proving the viability of using cutaneous haptics in robotic teleoperation. We used two cutaneous fingertip devices worn on the index and thumb fingers to control the motion of a robotic hand and receive at the same time feedback about its interaction with the environment during this peginal task. Each cutaneous device is composed of 3 motors, you can see here, actuating a rigid platform on the user's finger. Now, this this feedback then provides in a way a one-to-one localized cutaneous information about the contact forces registered at the remote side by the robotic end while holding this peg. And results showed that cutaneous-only cues can provide rich and effective feedback on the forces exerted at the remote side without needing any additional stability control, even in the presence of these contacts or delays. However, providing cutaneous feedback also led to higher forces applied to the peg with respect to providing kinesthetic feedback to 2 standard grounded kinesthetic interfaces. So after this first work, we applied the same concept to robot-assisted medical palpation. The same cutaneous fingertip device, augmented also with a vibrotactile motor under the platform, you can see it here. We mounted it on the console of a Da Vinci surgical robot. This device again provides contact deformation and texture sensation, this time at the operator's fingertip, about the interaction registered by a biomimetic tactile sensor here, mounted on the Da Vinci surgical tool. Now, all this we did it during the palpation of a soft tissue phantom that had inside, it represented a heart model, and inside we placed a rigid plastic stick that represented the presence of a calcified artery. Now, results of this showed, so the task was to palpate, of course, this phantom to locate where this, the rigid plastic stick, the calcified artery model, was hidden. Results show that providing cutaneous feedback significantly improved the performance of the palpation task with respect to using only vision, which is nowadays what happens in Da Vinci surgical robots. And this led to lower localization errors and lower applied forces to the phantom. So contact deformation feedback provided by the moving platform seemed more important than vibratory feedback provided by a protactile motor. But actually we saw that this depended very much on how the users explored the soft tissue phantom, which I think was very interesting For example, for dragging the sensor across the fundus, the transient information delivered by the vibrotactile device was more important than deformation feedback to locate where the calcified artery was located. So this result really showed the multifaceted nature of our haptic sense, which makes choosing the right type of feedback not very trivial. So it's very important to run many experiments and try to understand where these results come from. Now, very well. So now in this two-fold work, I showed the viability of using cutaneous haptics for rendering physical properties of the environment. So, but in our results, in our research, we have done a lot of this, right? And we have registered similar results on many scenarios in industrial training, robot-assisted insertion, cutting. So if you're interested in these, please get in contact with me. Haptic feedback can, however, also be used to provide abstract information during the teleoperation, such as navigation information. So I wanted a bit to talk about this. For example, in this work, we use haptic guidance to help a human operator during a pick-and-place task using a robotic arm equipped with a parallel grip. Kinesthetic feedback provided by a grounded kinesthetic interface here guides the user to grasp objects for a set of predefined good grasping poses. You can see them here in blue. Grasping poses that ensures a firm and safe grasp of the object at hand. At the same time, cutaneous feedback provided by an armband informed about the vicinity of possibly dangerous configurations of the robot, such as singular configurations of the robot, but also workspace limits. So in this way, we can provide multiple pieces of information at the same time. Cutaneous haptics paves the way to provide these multiple pieces of information at the same time, leveraging the large size of our skin. Results will show that this works, leading to smaller completion time, shorter trajectory, with respect to employing standard human-in-the-loop teleoperation. And of course, this can be also extended to consider more complex metric, including the effect on the grasping on some post-grasp trajectory, or on how the movement of the user affects the fatigue or the attention of the user, especially for for teleoperation that last a long time. And we are working a lot on this. I'm already probably over time, so I will be very quick. I just wanted to mention a few other areas in which we apply this kind of approaches. We have been working on using ultrasound media haptics to provide the contactless cutaneous haptic sensations in virtual reality as well as in teleoperation. We have been using cutaneous haptic bracelet for providing situational awareness during human interaction with multi-drone systems and during the steering of assistive mobility devices. And finally, we've also been working more and more on micro-robotics in the scope of a large-scale European project for using haptic shared control for the intuitive control of multi-robot systems at the micro scale. Now, our grand objective is to achieve superior human-robot interaction and collaboration through the sense of touch. One last minute, Giacinto, if I can. I have two take-home messages. The one is that haptics is very important. We are really craving haptics. We are craving contact with other people, and we have seen this during COVID, for example. But despite this, haptics is missing from most robotics and interactive application nowadays, severely limiting the potential of this technology in interaction technology. So it is important to know how to study. It is important to study how to design effective haptic interfaces. And haptic interfaces can make the bridge between humans and robots, because we want to empower humans through robotics, not replacing them. And haptics and sensory feedback is a way to do that. The second and last take-home message is that very often less is more, especially in haptics. We cannot wholly recreate the intricacy of our tactile interaction. So for each scenario and task, it is fundamental to study the most salient and representative pieces of information and then focus on those to develop specific haptic interfaces and rendering techniques good at eliciting such a relevant subset of haptic sensation. And cutaneous haptics is very promising for this, simple yet very, very informative. So this is a picture of our group. So if you want to interact with this, we are working a lot on all these topics. So please get in contact with us. We are organizing also a conference next year in Italy, in Siena, EuroHaptics 2026, with deadline in January. So this is our projects and our funders, and that's everything for me. So thank you very much for your attention. And if you please get in touch with me if you want to.
Thank you very much, Claudio. We have 1 minute for the Q&A.
I could ask a question, but I will let other people first, since we've got quite a few people now on there. If there isn't any, I'll just start, and if we've got time, we'll ask other questions. Yeah, thank you for the presentation, Claudio. Really interesting. I really appreciated the part when the last 2 slides when you put sort of showcase the importance of having humans, or how important haptics is for the human sort of interaction. And on that side of the problem, I want to ask, how do people react to, or what feedback did you get from people on the technology they developed, especially the cutaneous one that you created? Because, for instance, if you think about VR has been about for a long time now, a long time in relative terms, but then people don't tend to use it for a long time because it's not really an enjoyable experience, because it gives nausea for long term, gives headaches. So what did you get? Did you get feedback from people? And what was it? Doctors that were using it? Was it like users, random users? And what did they say about using it? What was their experience?
Yeah, thank you for this question. So first of all, cutaneous haptics is very broad, so it can be anything, and we are using it every day. So our phone that vibrates provides vibrotactile haptic feedback. So we're getting more and more used to receive this kind of sensations. In my opinion, what we should aim to is having devices that do not impair our capabilities to interact with the surrounding world. So this is why I'm not, so they do work well, but I'm not the biggest fan of, for example, of gloves, right? Because when you put on a glove, then you just use the glove, for example, in VR. But you cannot do anything else. You have this big glove that impairs you. While if you are provided with the rings or with glasses or with bracelets, that they provide information in a very private and discreet way. And this people really like, and it's very well appreciated. The vibrations are great, but sustained vibration can become annoying very quickly. So we are working more and more on more skin stretch, gentle tapping. It is very important to study pleasurable feedbacks also.
Thank you very much.
I think I finished my time.
Okay.
Thank you everyone.
Thank you very much, Claudio. Let's start with Antonia now. Professor Tsemanaki.
Yeah. Hello, everybody. I'm just going to share. Hopefully you can see that now.
Yes, we can.
Yeah. All right. Thank you. It's good to be here, and thank you for the invitation. It's good to see some faces that I know and some new ones as well. So I am associate professor in robotics, and I'm based at the Bristol Robotics Laboratory in Bristol and the University of Bristol. I'm leading the dexterous manipulation and wearable robotics group at the University of Bristol, which is a group of about 10 PhD students and 2 postdocs. Our website is, you can see it here if you want to know more, and my email as well to contact me if you want after this. So this is what the Bristol Robotics looks like at night. We like to have some robot arms holding lumps and illuminating the space. Bristol on the right side on a nice sunny day. It's not very often that happens, but when it does, it's beautiful. So this is some of the areas that my group is working on. So we're doing a lot about dexterity, and dexterity for us means a lot of things. It means multi-finger hands, it means exoskeletons, it means touch, and it means teleoperation, of course. And teleoperation, we apply that in both the medical field, healthcare, rehabilitation, physiotherapy, surgery, needle insertion, diagnosis, biopsy, but also environments that are extreme, such as space or nuclear. So these are some of the projects, sort of as an overview, because I don't have time to speak about everything that we do. I've chosen just 2 areas to speak later, but you can see here that we develop our own exoskeletons and our own gloves. We started with 3D printed and rigid materials, and we've moved on to more soft, hybrid, and flexible materials. We play a lot with silicone sheets that we then laser cut or blade cut to create our gloves, to make something that is cheap and easy to manufacture and really fits the user's hands perfectly. We have a big part about developing and mimicking the human anatomy, developing basically organs such as bladder that you can see here at the bottom, as well as the lungs and the pleural space outside of the lungs and the rib cage. And on the bottom left here, you see a version of the pelvic floor, where we are trying to simulate the musculature anatomy, the muscles of the pelvic floor, and how we can then create simulators that train doctors and physiotherapists in treating patients. So in teleoperation in medical interventions. So as I said, we're looking at surgery, telemedicine, diagnosis, and for that, we develop our own soft tactile sensors. I started this in 2016, quite many years now, in my PhD about surgical applications and minimally invasive surgery, for which I wanted to create a system that was multi-finger, multi-dexterous sort of abilities, provision for haptic feedback, but a system that would be portable and adjustable and fit the surgeon perfectly. My goal was to try to get the system to adapt to the surgeon rather than the surgeon adapt to the systems, like, the Da Vinci. So I created a miniature surgical instrument with 3 digits that was multiple joints. In total, it had 13 degrees of freedom amongst 3 fingers. And then to operate that, I created a glove exoskeleton. So you can see on the right side a sort of an idea about how it would work. It would enter the abdomen and unfold, and then the teleoperation would happen by the surgeon. So a bit of a close-up of the exoskeleton. This is quite old now, but we've developed on it. We've changed the materials. We made them soft, hybrid, different materials, playing around with, and different sensors. We started with Hall effect sensors, which were really good and really sub-degree accuracy. But the problem is that they could only fit when it was rigid structure. So now we're using IMUs and flexible sensors. So we were also been interested in the past 5 years now on telemedicine and diagnosis. We looked a lot into breast cancer, early detection. So for that, we developed a series of soft tactile sensors. So you can see how we started off on the left side. We basically made a haptic little device that would inflate and squeeze, inflate, deflate, which means change the stiffness of its membrane, and then squeeze the fingertip to create these 2 different modalities. It gives you different sensations about whether you're touching something hard or soft, rigid or flexible membrane. And then we took that sort of concept to create these 2 different sensors, one which we named espresso, and the other one that we named new tip, because they are both pneumatic. So the idea for them is that these sensors have this sort of soft membrane that can inflate and deflate, and that basically creates the membrane of a variable stiffness. But then what happens with the sensor is that we can tune the range of the sensor, and we can tune its sensitivity. So this is where the eustachian tube inspiration, because the eustachian tube is the little tube that we have between our nose and our ear, which when we are going up in a mountain or down below sea level, it basically equalizes the pressure, and you can basically sometimes hear this popping in your ear. So this is the same style here, the same inspiration for the function of these sensors. So you can see here this pressure sensor tapping on on a piece of a slab of silicone that has embedded nodules in it on the size of this little sphere here. And I can then basically find these nodules, recreate them, and it can also be more accurate than the human finger at this point. And the uniqueness of these sensors and the novelty was that they're not a tactile sensor that can just feel the surface of an object, but because of the potential they have on changing the range and the sensitivity, it can detect objects that are really deep into the layers of the object. And this is why we looked at this at breast cancer, because nodules in a breast can be very, very deep in the layers, and these are the ones that are missed most frequently. So moving on into teleoperation now, a little bit further from the healthcare field, we looked at space and nuclear applications, and especially in glove boxes, teleoperation in glove boxes when you have limited space, but also teleoperation when you have a delay. So we're talking about delays, for example, in space, where we have teleoperation between Earth and orbit, Earth, Moon, or even Earth and Mars. So you can see that the delays there really, really are different. And we started this in I have to say, quite a naive idea about, haptic feedback will solve it. Haptic feedback will be the mitigation to these delays. And then we found that actually it can make things worse. But there's a golden sort of limit where haptic feedback makes things better, and then beyond that delay, it makes things worse. So we did objective studies and user studies where we asked students, users to do different tasks, and we tried different delays. And then we also actually interviewed experts that are using robots or machines that they teleoperate them in 4 different areas. So we looked at the nuclear reactor maintenance, we looked at underwater exploration maintenance, explosive ordnance disposal, and we looked at 3 surgeons. And I'm just going to go back to the previous slide just for a second. So I think the takeaway message here was that these 4 very different areas had very, very similar requirements. And you might think that surgeons really don't belong in this area, but they had the exact same requirements apart from one. So the surgeons would refuse completely to operate on a patient if there were delays. Well, the others were used to this and have already developed different strategies to mitigate such delays. So then to test these ideas a bit more and explore how we can use haptic feedback to actually mitigate these delays, not in a naive way anymore, but in a little bit more of a complex and strategic way, we took the task of simulating moon dust regolith in a glove box eventually. So we used an existing model that was the Pereira and Schmidt model that was published in 2021, and we developed it to be real time, so we simplified it. Then we used this to verify it experimentally by basically pouring regolith in the lab through these funnels that you see here. And finally, we use this in a model-mediated telemanipulation system. So basically now we would have a cooker robot with a scoop doing different tasks that you see, like press, drag, scoop, or scoop and then drop it on a set of scales, while the user would manipulate teleoperate the KUKA robot using a haptic device, and they would basically see in real time the delayed system, but they would feel what was happening as if it was real time, because we had the model. So using the model, we would apply haptics to the hand of the user, but they wouldn't feel the effects of delay on their hand, but they would only see it. So this combination basically improved the accuracy and helped them carry the task better. So I did mention Glovebox. So we haven't combined the studies of the trustworthiness and the haptics with the Glovebox, but this is our next step. So what we have done in the Glovebox basically operation is to try to put a big robot and a big complex redundant robots like the KUKA in a very limited Glovebox, and try to understand how we can use that without having it colliding with the walls of the Glovebox. So this is work from my PhD student Kat. She basically mapped and developed a 1 billion poses database for KUKA, and she used that then to in an autonomous way operate KUKA to go to specific positions without colliding with the Glovebox. So you can see here how it goes from an A to B basically position, a trajectory without the Glovebox, but assuming that there's a Glovebox. So we just, for visualization purposes, we've moved the Glovebox here. So I'm hoping I think I'm going to stop here, try to go very quickly through some of the research. I'm happy to take questions or, be connected later. Thank you very much.
Thank you very much, Antonia. So, questions?
Yeah, thank you, Antonia. I want to say, you took us on a journey. You took us from an operating theatre back to Earth, and then again to the moon. So it was really interesting. I've got a couple of questions, but there's one on the chat first. I think it's from Radhika. She's asking if the optical tactile sensor is an adaptation of TACTIP, or is the one you presented something different?
It's different to TACTIP, but good spotting. We got for the new tip, which is the one on the right side here. It was inspired by TACTIP, but TACTIP is not pneumatic. So it has the same style of this sort of papillae inside, and they're locked by a camera, but it can inflate and deflate. So this was what was new from the TACTIP. Then we sort of moved on from this style because we wanted to miniaturize the sensor. So you can see the espresso is much smaller, and in fact here I don't actually show the final version. So I don't know if you can see my camera. This is one of the versions here. This is what you see in the screen actually now. So this is about 15 millimeter diameter, but at the moment we have a version that is 6 millimeter diameter, and we actually apply this at the tip of a pen to use it for braille tip reading. And so the idea that we moved on from the optical to the fluidic, which is the espresso, is because we removed the camera from the sensor. We had an umbilicus. We have the camera completely far away from the sensor now, and we can miniaturize it really, really, really small.
That's interesting. Thank you very much. I've got another question on that, if you've still got time. So in the next slide, you were showing sort of the information that, so I can see is a very complex system, and the sensory data they can get is there's a lot of information there. How is that conveyed? Because I can understand how it can be understood by a robot by doing some interesting maths and everything, but how is that information, how is that conveyed to a human? How can a human understand that sensory feedback?
A good question. So here we show a version of the sensor that has basically 9 tubes coming out of it. Each of the tubes has this black, basically water dyed with black dye, black food coloring. And this is not using machine learning. It's using very simple image processing techniques. It can track basically when the tube when the fluid moves, and then converts that into a value. We calibrated that using force torque sensors and springs, and it isn't very complicated. But the idea that I don't have this in the slides was to combine multiple of those sensors and put them at the same time palpating a complex object. So we have, for example, a breast. You can see here on the top left and how we can palpate it. So we would have at least 5 sensors around it palpating at the same time, getting information from the same object, but different aspects of it. So this is where it gets complicated. So for this, we were going to use machine learning to try to look at the redundancy of all this information for the same object, and then try to create a heat map of the inside volume. But this is future work again. We haven't quite got there.
Perfect. Yeah, thank you very much. Any more questions from the chat before we move on?
Okay, I think, Carol, it's your time. Thank you very much.
Good morning, everyone. Let me just share my screen. Yeah, thank you for the invite. I'll start with a little bit introduction about the MTC and what we actually do, and some examples of our case studies working around telerobotics. And I'll maybe start talking about the future direction in the industrial context, where the telerobotics might play a role, at least in my mind, and where it contributes. And I'll finish with a bit of a introduction to the EU robotics topic group and some of the activities that we are hosting in the near future. So start with introduction. My name is Karol Janik. I'm technology manager at the MTC in the UK. I'm also co-chair of EU Robotics Telerobotics topic group that I'll talk about in a second. But to start a little bit about the MTC, we are an independent RTO in the UK, similar to other RTOs across Europe. We've been around for over 10 years. Now we have over 1,000 members of staff, so we grew quite quickly. And our role is really, it's all about translating innovation into real world industrial application and boosting industry to positively impact society. And over 10 years ago, we started working very closely with aerospace sector, but over time we really diversified into working with pretty much every single sector of industry, which gives us very good overview on different challenges and different technologies used, and cross-sector transfer of technology while working closely with academia, of course. And in terms of automation robotics, our core objective really is to increase the number of robots in industry in the UK through different streams, providing overview to the art of the possible. So working closely with academia, educating industry on what's out there and what's on the horizon, developing new solutions, new technologies that will support productivity, safety, and other KPIs in the industry, helping companies find the right solutions for the problems and the right innovation for the problems, and support the development of the supply chain. Because with the supply chain, we can't really scale up or deploy robotics that well. And working in challenging environments is one of our key focus areas beyond kind of classical in-factory manufacturing. And it's all about enabling productivity, safety, and reliability of critical national assets, infrastructure, and building better supply chain resilience. So a lot of work that we've been focusing on is autonomous and automated inspection, remote operations and remote handling, autonomous and remote servicing and maintenance. And that's across multiple sectors that fundamentally have very similar challenges. So sectors such as nuclear, construction, infrastructure, agriculture, pharmaceutical sector. And on the bottom, you can see some examples of the work around remote operations, remote and autonomous inspection, or autonomous operations in food manufacturing, in that case, fruit picking. But with some examples from the telerobotics itself, very similarly to what Tanya showed around glove boxes and teleoperation in confined spaces. We've been quite active in this space for a couple of years, working especially with nuclear and pharmaceutical sectors. But our focus is much more higher TRL, much more industrial, and it's all about how we deploy fairly mature hardware in bespoke settings to fundamentally move operators away from the hazards and increase productivity and safety of various processes either in nuclear or pharmaceutical sectors. So some of the projects that we've been working on in the past is around glove box automation and remote operations within the glove boxes. So we developed a series of mock-up glove boxes with different robot systems remotely controlled by the operators. We primarily used force dimension haptic device, integrated haptic feedback, kinesthetic haptic feedback. So operator could feel the forces, the inertia forces of the robot and the grasping forces from the gripper. We've been doing quite a bit of work around the operator controls and the perception of the operator, because that's always been quite a big challenge. So that's kind of some examples of work that we did in kind of classical teleoperation in the industrial setting. We haven't really done much about kind of low-level haptic feedback or really tactile feedback. We never really got to that level because, at least in the use cases that we looked at, it never was needed fundamentally. But I'll get into that in a second. Get back into that in a second. Other example of our work is a bit further from classical teleop. So that's an example of our work, again, with nuclear sector, focusing on autonomous sorting and segregation of unknown waste objects, which finished with industrial demonstrator with one of the tier 1 suppliers that are further maturing it towards commercial application. System is basically autonomously recognizing, segmenting different objects, coming up with grasping strategy, picking objects, moving them to different sets of sensors to get the volume, get the radiation sensing, recognize the materials, and so on. But it's all supervised by the operator for a couple of reasons. One of them is supervision of training for the autonomous operations. So from labeling, grasp poses, and so on, operator has supervision over that and supports development of the autonomous systems, of an autonomous solution. But when the operator sees that, for example, grasping strategy doesn't seem right, that's where he can step in, change grasping poses, and let the system get on with it. And again, that feeds back into the training strategy. And there is opportunity for operator to basically step in and tally up if possible. But that's kind of not the core foundational idea of the work, because with a lot of industrial solutions that we see, it's all about deploying things at scale, as I mentioned earlier. So if something can be automated, if something can be autonomous and supervised by operator, that's something that we are effectively aiming for. And that leads to kind of some of the other examples of our work around different remote facilities. And I have two examples here. One is the research facility that we very recently commissioned, focusing on dismantling and assembly of live EV batteries or batteries, which obviously comes with a great risk for everybody, for anyone who's involved in this process. So we built this facility that has all the safety fire suppression systems and so on, with two large robots and whole suite of tools. And the facilities designed to be automated or autonomous in the long term. The challenge with EV batteries is that every single one can be very different. You can't really hard automate it. That's where our focus goes towards autonomy, and that's where teleop can play its role. So either sharing the tasks, so there is some automation for things that we can deal with that we know, there is some autonomy for some other tasks, and there is an opportunity for teleoperation. And that kind of goes together with the general trend that we can see around robot learning and using teleoperation as an input into robot learning, especially for things like vision language action models. Probably many of you seen mobile Aloha system, and this approach is used by many people with teleop as an enabler for our autonomy. And from my kind of industrial perspective, that goes back to the scalability. If you want to have 100 of those facilities deployed somewhere, you don't want to have few hundred people with very high level of expertise that have to look after them all the time. But rather than this, you can't really get them, you can't really afford them because of this skill scarcity. So the challenge is about having a small number of very specialized operators looking after a multitude of facilities, and that's where I think supervised automation with opportunity for sharing tasks really plays its role in the industrial setting. So that's a very quick whistle-stop tour of some of the examples that we've been working on. I'm happy to take questions in a second, but yeah, just before we finish, I mentioned in the beginning I'm co-chairing EU Robotics Association Telerobotics topic group together with my two much more smarter colleagues, Alois from CERN and Daniel from DLR. So we've been running this group for a couple of years now. It's a group open for public. You have a link on the bottom of the slide that leads you to EU Robotics portal. You can access topic groups there. EU Robotics Telerobotics topic group have way over 100 members, and it's effectively kind of grassroots community movement. A lot of people on this call has been involved in it in some shape or form. So feel free to join, feel free to drop us a message. But more importantly, and we will be sharing that publicly in the next couple of days, on the 5th and 6th of November, we will be organizing a public workshop at CERN in Geneva, focusing on telerobotics. So the spaces will be quite limited, but we'll have effectively 1.5 days of expert talks, breakout sessions and discussions, and various tours of CERN facilities, including the remote robotic maintenance that Alois is involved with. So more details to follow. I'll definitely share the details with Jacinto and Gianmarco. Yeah, that might be a really good opportunity to see some of you in person in the next couple of months. So yeah, that's briefly about what I do and what we do at the MTC and EU Robotics around the topic. So I'm happy to take any questions now. Thank you.
Thank you very much, Carol. Let me take advantage of the fact that you were mentioning the EU Robotics group you're leading on telerobotics, for thanking you also for the support on spreading the news on the conference on IEEE telepresence for the next month in Leiden. That is also supporting this webinar. And any questions, anyone? Just we have time for one before the panel.
Yeah, I'll break the ice before people ask another question. So Carol, obviously it's slightly different because you come from mostly an industrial perspective. So what do you think? We don't see enough teleoperation in industry. What do you think are the sort of hesitations and the obstacles on that? Is it mostly culture, or is it just because the technology is not quite there yet?
I mean, it depends really on the sector. I think it is quite specific technology. I think with sectors that have effectively large numbers of robots like manufacturing, it goes back to what I mentioned. It's purely the scale of things that you want to operate. But in industries where you effectively run single systems, I mean, nuclear is a great example, you know, fusion and great work that UKRAS and RACE are doing with and have been doing with jet decommissioning and jet operations. You know, you kind of have to do it remotely, and I wouldn't say there is any hesitation for it. I think there is hesitation for robotic systems in general, especially for highly regulated industries. So, you know, yeah, again, things like nuclear could be some of the defense work, could be pharma, could be medical, because you need, you know, effectively 99.99 reliability, and you need to go through, you know, all the safety cases and regulations, and very often there is a big risk awareness with just continuing doing things like we did with, you know, very simple mechanical manipulators or with manual operators, because, you know, the risk of doing the innovation is too high. So, you know, it's about balance and about, you know, what sectors needs what effectively.
Yeah, I agree. Thank you very much. I think we've got another question from Radhika from the chat. She's asking, Carol, were you involved in any exploration of impact of latency in teleoperation?
Thanks, Radhika. Not really, to be honest. I mean, there is a lot of good research going in this space, especially for medical and space sector. We haven't really been involved in this topic because for all the use cases, applications that we dealt with, I mean, they're effectively hardwired, either because they could be hardwired or, you know, end users not so keen on any kind of wireless communication, and it's usually fairly short distance. So, you know, you can deal with fairly standard IT infrastructure or direct fiber link. So, in any of our work, latency haven't really been an issue, but I know there's quite a lot of work going in this space across some research units.
Okay.
I have one question. So you mentioned sort of the application of robotics, telepresence robotics applied to different industries, which I have mainly sort of dealt with unhuman or unpopulated spaces, and with either constraint in a god blocks or in space, or in a more industrial setting where everything is sort of boxed within a certain space, in either through direct control, shared control, or supervisory control. Do you think there's a viability to expand this to social settings, or do you think it's more this technology is more suited to sort of spaces where not humans are involved?
I mean, I think so, but I think the real challenge is safety, especially, you know, in a social setting, and, you know, like looking at it realistically, things like grocery delivery robots, which is, you know, a wheels on a box, getting the public trust and regulatory set up right to deploy them in the public space is a massive challenge, and this is, you know, effectively a box on wheels. When it comes to, you know, more complex systems, and people obviously talk a lot about, you know, humanoid robots in social setting, in the long term, again, how you can ensure that, you know, even stepping away from the teleop, that the system is inherently safe, that it won't fall on, you know, on someone, that it won't hit someone. That's a massive barrier, and, you know, supervision or teleoperation might be one of the ways of justifying or going through that safety case, that it's not, you know, autonomous or automated system in the wild, but it's supervised by someone. I think, you know, in some way the technology itself is not a blocker. It's about how we ensure it's safe and reliable. I don't think we are in this place in any shape or form for social or public setting, because, you know, in industry you have risk assessments and regulations and processes, and you know, you have machine directive you have to follow, and so on and so on, and you do everything to ensure safety. it's not easy to do that in public setting. So that's a big challenge.
Thank you.
Thank you very much. More questions? Okay, let's start the first round of questions for every one of you. Claudio first, then Antonia, then Carol. I have one because the time is really short, and since telerobotics, teleoperation, telepresence are topics that are typically bringing the robots outside the laboratories, even during research investigations, and you need to consider the point of view of users, stakeholders, while you're also considering theoretical aspects, or let's say something more related to the cognitive processes and the perceptual processes of the user. What are the main challenges you found in discussing with such a complex, the actors in this such a complex context? I mean, on the one hand, you need to consider the cognitive processes and the mental processes of the user. On the other hand, you need to consider the needs of the users and in the real life and the stakeholders' requirements. Claudio first, Antonia, Carol.
Yes, okay. But what do you mean in the sense that if our research should be driven by actual needs, in the sense?
Yeah. The challenges you found in considering this complexity by discussing with the stakeholders, I don't know. The first challenge you have in mind.
Yeah. So we have been working, for example, a lot on the handling of dangerous materials, which is something that is very interesting. And yes, there is a bit of a clash very often in the sense that we like to do research on on things that are new, and then very often the industry is very well behind. So there is this gap, right? So we don't want to simply work on implementing a solution that has been presented in a paper 20 years ago. We would like to do something scientifically new, so that provides a scientific contribution. Very often the stakeholders, what they need is something that is working, and so there is a bit this divide, right, in what is interesting for research and what is interesting for the industry. But there are more and more approaches and techniques to do that. At INRA, at CNRS, we're working more and more on agencies that bridge this gap. Of course, for example, COA, that is very well known, CETIN, there are very different agencies that their objective is this. So they are engineers that bring research and needs together. So I think we are going in the good direction with respect to this. And we also have to make an effort sometimes from our side and make maybe things that are less challenging from a scientific point of view, but they can bring a real contribution to the industry.
Thank you. Antonia?
I do agree. We have to make an effort. And so in my group, we're sort of used to this effort in terms of engaging with surgeons and patients. Maybe because we have the networks and we know what the roots for that is. There's also, at least in Bristol, there's specific organizations that are helping you reach those people. And where we struggled was when we wanted to find to talk to professionals, operators of robots and machinery. So this is a very specific case because these people not necessarily are, they're not going around academic circles or conferences. You might talk to the CEO of a company, but this is not the people you need. You need people who are actually down in the field. And this is where we really struggle to get there. We even tried to get astronauts in our research because, and we did have a pathway to reach them, but obviously they're just super busy people, right? So, it took more than a year to reach those 13 people that we got for the interviews. So it was a struggle. I don't know if I have any pointers on how to do this faster or better next time. I think every time it will be a struggle. Perhaps maybe this means that we need a route to this. Maybe we need companies to help us do this, or to have an organization that reaches those people. I don't know.
Thank you very much. Carol,
Yeah, I mean, it's a good question, and obviously my perspective is a bit different because we largely work directly with end users, and getting broad stakeholder engagement is the paramount. So what Antonia mentioned, getting operators involved, people that actually do the job, not just talk about it, is something that we always strive for. But it's much easier if you directly talk to the particular engineering group involved in the process, and you can link into those people. So it is extremely important, whether you do research or whether you do higher tier applications like we, to engage with those stakeholders. It's difficult to find to get any pointers, especially for scientific community. We try to do it as best as we can as an RTO, and now we can participate, beyond Horizon Europe in the EPSRC projects in the UK as an active partner, and we try to engage industry as much as we can and get the right people, into right projects. But it is generally difficult because many of those people, if it's not the key priority of their work, they need to find time to effectively spend with researchers, and that will always probably drop somewhere low in the priority list. So it's a challenge. We're trying to help with those things, especially on projects that we're involved with. But yeah, I'm afraid I don't have a golden recipe for tackling that.
Thank you very much. Let me add that according to my own experience with surgeons and with experts in safety and so on, sometimes if you find too enthusiastic end users, they have a big bias and they're not representing anymore the whole community of the actual stakeholders. So, Gianmarco?
Yeah, I've got one final question if we've got the time. So this is the, again, internationalization pillar of the UKRAS. So I want to ask a question about, and I'm going to have two perspectives, I'm assuming, one from the UK, from Carol and Antonia, and the other one from France, from Claudio. So what do you think organizations like the UKRAS, what could we do to sort of improve, not necessarily actual projects, but how do we get more people to get to know each other, people with common interests outside the UK? What sort of activities would you like us to organize for researchers, especially young researchers who don't know many people, to get to know other people around and around the globe, really? And what's missing? Obviously, there's, apart from projects itself and funding, what activities could we do to sort of make people meet each other? I don't know who wants to start.
It's a good question. It's a very good question. So I'm thinking of what could make me, for example, come to the UK and meet. I think, for example, inviting, having some very small funding to give to professors in the UK to invite international researchers. It's cheap because it's just travel, and could be a way to foster this. If you want to do a bit more, if you provide some money maybe to do a small course, an introductory course on a topic given by a international researcher, because it gives time and direct contact with students. So maybe this could be a bit more fruitful. Yeah, other people, I don't know if you have other ideas.
Maybe I can just, I do like what you said, Claudio, and maybe I would like to add to that and to say that it would be, I mean, I'd love to work more with European partners, and I already have some partners and some connections, but in terms of new ones, I don't know, maybe some support or some more making it easy for us. Brexit and the whole thing has changed a lot, and our universities do support us in understanding how things happening, but maybe sometimes making it a little bit more specific and explaining it to us when we have the European partners already, and explain it both to us but also to the Europeans. That might help. Of course, webinars like that or even in-person seminars really help. I was wondering if maybe in the future there's possibility to do some sort of brainstorming or what do you call them? You call them sandpits, with very small funding to just get concept ideas together to spark these sort of future collaborations. Maybe that would help.
Yeah. And another thing could be, you know, for European projects, for collaborative projects, to be proactive in trying to build the consortium. So you have, let's say, Giacinto, who wants to coordinate a European project. Then and he's looking for some expertise. So you can keep a pool of experts in different fields, so that you can help, especially younger PIs like Giacinto, to to find the right expertise, right? So he's need a certain expertise that doesn't know anyone. He contacts you. You have a pool of contacts. This could work.
Sorry, I must correct that young is said.
I said
Let's
young.
proceed with Carol. You're
Yeah,
probably
it's
younger
younger
than me.
than somebody else.
I stopped to be young when I was a child. Carol?
Yeah, I mean, if I can add something, you know, things like this webinar, and I think what you guys started doing quite well is tapping into existing networks. I think, you know, this is a powerful thing in the end, because, you know, you have IEEE, you have organizations like EU Robotics, you have UKRAS, and then there is probably, you know, a dozen of other networks of groups. Creating some kind of connections between them and creating an opportunity, even like this webinar, for people to, you know, get known each other and talk to each other is a great first step. I mean, that's one of the reasons, you know, why we're doing this webinar at CERN, is to, you know, meet in person. We every year do robotics workshops at European Robotics Forum. So that'll be, you know, quite well attended every year and gather very different people every year. But it's not something that happens overnight. And I think just, you know, keeping people engaged and keeping connections alive is important if you want to keep those, especially international connections, running well. And then there is the whole in kind of funding and formal side of collaborations, which is, you know, a bit difficult to navigate after Brexit still. I think we all agree that, you know, the current program in the Horizon Europe is quite complex to navigate when it comes to topics and funding streams. We'll see what the next work program will bring. Hopefully, it will be more simple to navigate and with more opportunities. But, you know, there are things like CDTs in the UK that are good at often, you know, bringing international students and creating some international collaborations. So, you know, pursuing those is a good way of keeping those networks alive in practice. But I mean, obviously, you, Claudio, Antonia, and the rest of you have much more experience than I in all of this.
Well, when there will be the next European Robotics Forum in the UK? Because you're going to organize it. So
yeah, that's you don't need to remind me.
I want to remind for the others.
Yeah, no, that's March 2027 in Birmingham. So again, that will be a good opportunity to get everybody together in person. So yeah, it's 18 months ahead, but that will go very, very quickly.
And there is plenty of work to do. Let's do it together. About UKRAS, anyway, just remember that there will be the event in Nottingham in the 11th, right, Gianmarco, of September.
Yeah.
We wait for you there. And more questions from the audience? Quite a quiet audience. In my opinion, what?
I'll do a question. So,
Yeah,
well,
thank
first
you.
of all, hello everyone. Probably no one knows me. I'm my name is Samuel. I'm a PhD student at Cardiff University. Currently focusing on developing mobile immersive telepresence using supervisory control for social settings. And currently, I've been sort of having a little bit of trouble trying to sort of properly align my research to be able to make like high level, high quality contributions toward this field. And although my attempts to reducing different parts of the whole telepresence infrastructure have been made, I still feel I'm sort of having some problems sort of dealing with properly grounding my research into specifically making proper autonomous systems for immersive telepresence applications. So in these attempts, I've tried to sort of restrict the ways of the user visualizes the environment and the communication protocols towards the towards the autonomous systems within the robots, and within the autonomous systems, I'll also constrain some different parts by only utilizing the state of the art within those respective fields. But in this regards, do you have any advice into which parts I should try to keep at par with the state of the art in order to sort of make a significant contribution in a specific area of the telepresence system, such as the autonomous cell?
Who wants
Thank
to
you very
take
much.
that?
Sorry,
I was saying, who wants to take that?
Oh, it's a bit of a difficult question. Oh, sorry
It's
about
a
that.
lot, yeah. It's a lot to answer in
Yeah.
short.
I had to take
it-
notes actually, but it's up to the speakers, not to me to respond.
I think to say that we're very happy to hear from you. I don't know. Obviously I'm biased. I can send you. I mean, if you saw my talk and you can see the recording, I've got some links there about work that we've done, and then maybe if you look at them, you can look at the trustworthiness side. I think that's a big field that has been explored, but not adequately. And I think more needs to be done on that. I think glove boxes are another area, and I think that industry is always very interested in that and how to improve things and teleoperation in travel, especially because it just makes things much cheaper and much more accessible to everybody. So we got inspired to work on this topic when we were looking at the Mars rover return, and there was just not enough time and materials for everybody on Earth to work on this. So we were looking into glove boxes with NASA and ESA because of that, because we wanted to give accessibility to everybody to access samples. Maybe someone else has some suggestions about areas.
Yeah, I mean, it's difficult to pick one. I mean, there is, from a bit more industrial perspective, there is a big white elephant when it comes to robots in hazardous environments, and that's hardware. A lot of research is done on kind of standard industrial equipment. There is some development on effectors or controllers. But then when it comes to particular challenges that industry might face, I mean, Glovebox is a good example. People try to put standard industrial robots into Glovebox into certain scenario, but then you might have inert environment with specific gases, radiation, and other things, and is the standard industrial hardware a good fit to tackle those environments? Manufacturer won't tell you because they're not designed to do that really, and it's not in their interest. So hardware for hazardous environments or teleoperation in general is a big white elephant. Is it the right research area or novel enough? Probably not.
I would say go for something that you like, that really excites you. I think this is the.
Sorry, I think at the end probably convey my question. So currently, basically, what I'm trying to do is make remote visits to museums more easily, and to do so, I'm sort of increasing the level of autonomy of the robot and utilizing supervisory control to do that. And sort of, I've been having troubles trying to make this publishable, and I was trying to sort of came here to ask the question if sort of some tips to be able to make this which parts of the systems should be constrained to a certain parts to be able to sort of make a significant contribution towards that field without being tackled from the other parts of the system. Because currently, when I'm sending a paper is either I send in it and I'm getting feedback from, okay, so this part of the system is not correlated to, is sort of, they think it's a contribution, but in the paper I'm sort of talking about it in a way that is, I'm using that part instead of contributing towards that part. And I don't know in which way sort of from which way should I convey these parts to be able to make it properly sellable towards conferences.
I don't think there is a rule. Right? I don't think there is a receipt. Otherwise, all our papers would be obvious. I'm joking. But I think in general, what you need to convey is that there is a scientific contribution. So I would say that you have to be careful to not make you look your paper as a technological improvement. So this is very important. So it's important that it works, but it's really important to advance in the state of the art in science. So it's not just a better implementation or incremental work, because it's something that we tend to do. Right? So we just add something and then we try to publish. And we should also not try to send a paper when you think it has a strong contribution, not just the minimum to publish. That is also something that sometimes we tend to. Then again, how to judge this? This is very hard, right? It's a bit of everyone to do. It's about experience. Of course, your PIs will have experience with respect to this. And reading other papers is very important. The more you read other papers, the more you can learn, especially good papers. I'm trying to get award-winning papers and so on. So how they are written, how they present, because also presenting them and highlighting your contributions.
Thank you very much.
So, more questions? I would say that we should thank you for attending and participating into this webinar. And next one, organized by Gianmarco and me, next month we'll talk about industrial robotics with the participation of researchers from the University of Liverpool, from the Canadian Research Council, and from the Health and Safety Institution in Germany, the BAUA. Stay tuned for having more information. And thank you very much.
Thank you.
Thank you.
Thank you, everyone.
Thank you so much.
Bye.
Thank you for organizing.
Thank you. Ciao.
Thank you.
Thank
See you
you.
later.
Ciao.
Thank you. Bye. Ciao.
Thank you.
Hi, Henry. Thank you.